Okay, Math 156, I'm going to go over the solutions to the problems on the review for the midterm. So problem 1 was to compute some limits in infinite series. So let's just take a look. We want the limit of 1 plus 1 over x raised to the power x as x goes to infinity. And I write this with a capital L. It's the statement of the problem. And if I write it with a lowercase l, I get the answer. E, well, that's nice. And if it's the same problem, but 1 minus 1 over x, then you should know from calculus that this limit is equal to 1 over e, or e to the minus 1. And if we take the limit of 1 minus 35 over x raised to the power x over 28. E to the minus 5/4. So in principle, you can do that just from knowing some calculus, but it's nice that Maple gives us the answer right away. We have two series. We take the sum of 1 over k cubed. K goes from 1 to 100. When I write sum with a capital S, again, it just states the problem. And if I write sum with a lowercase s, I get the answer. Get some humongous fraction. We want to know what this is as a decimal. I can do it in two ways. I could say, give me the sum, but EVALF. That means evaluate as a decimal or write as a decimal, whatever is inside. And so that's 1.202. So that's this finite sum. And if I want this, if I want the infinite series, I say k goes from 1 to infinity. And we get an answer which is kind of incomprehensible. So it's better. Oops. Infinity. That's better. There we are. Again, it's not clear what this means. I know what it means, but that's, we like it as a decimal. So let's just say, evaluate this as a decimal. Huh. 1.20200, 1.20205. So this is bigger as you would expect, but it's interesting that it's not very much bigger. Okay, that's problem 1. Problem 2 is to compute the first and second derivatives of some functions. So the method is the same for all of them. I'll just do a couple. So let's define the function f of x equal to the sine of x squared. So the derivative, first derivative of f, d of f of x, is that. And the second derivative is that. That's what it is. Let's do another one. Suppose we let f be x goes to the log of x. So this function has this as its first derivative. And that's the second derivative. And so on. They're all the same. Problem 3 is to expand a certain polynomial. So the polynomial is x cubed plus 1 times x squared minus x plus 1 times x to the fourth minus 1. If I want, I can just give the name. I'll just call it P. So if we expand P, that's what we get. That's multiplying it out. And if we want to factor P, we don't get this back because this actually factors. So when you actually factor this or this completely, this is what you get. 2, 4 is the product of these 6 different irreducible polynomials. Problem 4, we have a function which is a polynomial of degree 6. X goes to x to the 6th minus 17 times x to the 5th minus 45 times x to the 4th plus 132 times x cubed plus 5 times x squared plus 290 times x minus 456. X to the 6 minus 17 minus 45 plus 132. Yeah. And if we want to plot it, we just say plot f of x. And we get something that looks like that. And look how big these are. This is like 2 times 100 million. So hard to figure out what that is. Let's change the range maybe. Let's say it'd be plotted from x going from minus 25 to 25. Let's see what happens. Ooh, really shoots up. Let's put a range, some limit on the values of y. Say y goes from minus 100 to 100. What happens there? Oh, hard to tell. Let's go from 1,000 to 1,000. That's a little bit bigger, better. going down pretty far. Well, really hard to see what's going on. It comes down, does something in here, and then it goes back up again. If I plot it from -5 to 5, that's sort of what's going on in here. It's down. I just want to understand what's happening to this function. So let's look at it just from 0 to 3. Yeah, so in here, it's going up, up, and then it comes down. So it looks like it comes down, goes up, comes down again. No, but we want to solve the equation. F solve f of x equals 0 for x. Oops. Shouldn't even have been there. F solve f of x equals 0 for x. So this gives us 1, 2, 3, 4 solutions. -4, 1.2, it's in here. Yeah, so here you see what's going on in that area. There's a 0 where it crosses the axis, 1.2 and close to 2, exactly 2. That's where it is. That seems to be all the solutions. We just found them all. Okay. Problem 5, we want to plot two curves on the same graph. So plot, and then what we're going to plot, we put in curly brackets. And what we're plotting are 13 minus x squared over 40 and x cubed over 11 minus 8 times x plus 17. What's going on here? It's hard to see. So let's maybe plot it for x going from -20 to 20. So 13 minus x squared over 40, that's a parabola that's opening down. That's this red parabola. And this x cubed, that's a cubic curve going up. And these intersect in 3 points, here, here, and here. So let's just find the x's where they intersect. So F solve, I want to know where these two are equal. And they cross at minus 9.7, 0.5, and 8.9. There's a better picture. So here's the cubic curve. That's the parabola. They cross at least 3 points. Let me call them Z. Those are the zeros. So Z1, for example, that's the first. Z2 is the second. Z3 is the third. Actually, let me give them a different name. Let me call them X. So X1 is that. And if I want the coordinates of this point, I also need the y coordinate. And I get the y coordinate by substituting x into either one of these two equations. So I can say y1 is equal to what I get when I substitute x equals x1 into this equation. That's my y1. And it shouldn't make any difference if I also substitute it into the second equation. So let's just see. Oops. So if I substitute x1 into the cubic curve, oops. I should just give this a different name. I'll call this B. So X, oops. Let me clear everything. So this is my function F. This is X1 and Y1. And why doesn't this give me, why does it give me this? Let me try this differently. So that's my F. That's Y1. So if I substitute into the cubic, Oh, it's because x is, well, let me do it differently. There we go. I'm not sure why I had to do this such a complicated way, but. So this point is simply that where these two curves intersect, if I have x as the point, the x coordinate of one point of intersection, I get the same value of y whether I substitute in this or in this. And let's see what happens if I plug in x2. I should get a y2. x2 is 0.5. That's right here. And the value of y is a little bit more than 10. That's what it says. And if I take in x3 and I substitute that, oops. I know this is me. Here I should be substituting x2. That's 13. That looks a little bit better. And this is about 11. So these are the x and y coordinates of the 3 points of intersection. That's problem 5. For problem 6, we're going to use implicit plot, which means I have to open the plots package. So the command is with plots. And all of these plotting commands are now available, including the one I want, which is implicit plot. So I just want to plot the first curve to make sure I can make this work. This is x plus 3 squared divided by 20 plus y plus 4 squared divided by 80 equals 1. So we know that's going to be an ellipse. Let's say x goes from minus 10 to 10, and y goes from minus 10 to 10. Let's just start with that and then modify it if we have to. Now, I'm not sure why this doesn't work unless it believes X and Y have different values. So let me go back and clear everything from the memory. Open the plots package again. And plot, now it works. There we go. So I want to go down a little bit further. Let's make this 15. There we are. And I can really go from maybe, well, just leave it like that. So this is the ellipse. Of course, it looks like a circle. So if I do scaling constrained, now it really does look like an ellipse. There it is. But I don't want to do just the ellipse. I want to plot the hyperbola on the same graph. So we're really plotting these two. So I put them in curly brackets. That's one equation. And that's the other with a minus sign there. Oops. I forgot. Equals 1. There we are. Oh, perfect. So here's the ellipse. And here is the hyperbola. The red outside curves of the hyperbola, the inside is the ellipse. That's problem 6. Problem 7 is to compute some integrals, an indefinite integral and a definite integral. So int integrate, in parentheses, x to the 5th minus 2 times x minus 3, close parenthesis, divided by x cubed plus 2 times x squared minus 9 times x minus 18, comma x. Right? With a capital I, it writes down the problem. It doesn't show you the solution. But again, if I write this with a lowercase I, I get the solution. Huh, there it is. Sort of complicated, but that's what it is. And if I take the same problem, but I change the indefinite integral to a definite integral. So I want to integrate this from 0 to 1. I just say x equals 0 dot dot 1. X equals 0 dot dot 1. And this is the answer. If I wanted the answer as a decimal, I could just write EVALF around this. And this whole number turns out to be 0.177. And if I want instead to integrate one over x to the 7th, and now I want to integrate this, sorry, x to the 7/5, and I want to integrate this from 1 to infinity. That is what is called an improper integral. That miraculously turns out to be 5/2. Problem 8, we want to compute the area of an ellipse and plot it. Well, let me plot it first. I always like to plot things. So implicit plot. We're plotting the ellipse x squared over 63 plus y squared over 28 equals 1. Ax goes from -8 to 8, and y goes from, let's say, -6 to 6. That's my ellipse. Of course, I have to go to scaling constraint to make it look like an ellipse. There it is. That's the ellipse. And how can I find the area? Well, I can solve this equation for y. So let's say solve this equation for y. And we get, this is the top half curve of the ellipse. This is the bottom half. So if I integrate from here to here, this function, I'll get the area of the top half of the ellipse. Of course, I have to know what is the value, what are these two values? What are the values? What is the value of, where does this curve cross the x-axis? Where does it equal 0? When y equals 0, x squared is 63. So these curves are plus or minus the square root of 63. So I can say the area is equal to what? Let's say I compute the area of the top half and multiply by 2. So 2 times the integral of this expression for x going from minus square root of 63 to plus the square root of 63. Oops. This should be parenthesis there. Wow, 42 pi is exactly the area. That's pretty good. That's exactly what it is. Problem 9, we want to calculate a sequence. So in this sequence, u1, that's u square brackets 1, is going to equal 2. And u square brackets 2 is going to equal, sorry, u1 is 1, u2 is 2, and higher values, subsequent terms of the sequence, are defined by an equation for n from 3 to 30, that's all we go up to, do, and I put in my n do before I forget it. So un is going to equal 3 times un minus 1 minus 2 times u and minus 2. This is the sequence. Looks just like the powers of 2. That's interesting. That's what it is. That's very nice. Problem 10 is to find the smallest positive integer such that 1 over k summed from 1 to n is bigger than 10. So I could say, well, let me do it in several ways. And this is not the best way, but this is certainly one way that works. Suppose I take the sum, k goes from 1 to n. Sorry, the sum of 1 over k, k goes from 1 to n. It thinks n is 31 from the last problem, so let me erase everything from the memory. There we are. So let me give this thing a name. Let me call this a function s of n. So s of n is the sum of the reciprocals of the first n integers. So s of 1 is 1. S of 2 should be 3/2. S of 3 is 1 plus a half plus a third. It's 11 over 6, and so on. So I could do something like the following. Let me just erase this. For n from, let's say, 1 to 100 do, if s of n is greater than 10, then print n and s of n. And if oops, forgot a parenthesis. Nothing came out. That means s of n wasn't greater than 100 yet. Let me go out to 300. I'm sort of curious. What is s of 300? Ooh. Let me get this as a decimal. Well, it's only 6. I go out to 1,000, 8. If I go out to 5,000, it's 9. If I go out to 9,000, if I go out to 11,000, still not up to 10. 15? So somewhere up around 15,000 terms, I finally get a number bigger than 10. What about 14,000? Still bigger than 10. What What about 12,000? 9. What about 13,000? 10. So the numbers between 12,000 and 13,000. What about 12,500? So the number is somewhere between 12,000 and 12,500. Why doesn't it want to do this? Let's see, maybe because these numbers are so many terms. What about 12,300? No, it's too small. 12,350, still too small. 12,370, that's okay. 12,000, oops. 12,360, too small. So it's between 12,360 and 12,370. Let's see if it will do this for me. No, I can't do it. I'm not sure why. But we know where to look now. So this is too small. Let's go to 12,365. Still too small. What about 12,369? Ah. 8? No. 7? No. 6? Ah. So when I evaluate this sum for the first 12,366 terms, it's less than 10. 12,367 terms is bigger than 10. So the answer is 12,367. Now, just have to play with the computer to figure out what to do. Oops. So this is the last problem. Problem 11. Count the number of primes of the form n squared plus 7. So let's start, let's say n is going to be the count. We start with n equals 0 because we don't have any numbers of the form n squared plus 7. For n from 1 to, how far are we going to go? 1,000 do. And then this is n do. And what do we want to do for each of these 1,000 integers? If is prime, that's a function that's true or false, depending on whether the number you're evaluating is a prime or not. So if n squared plus 7 is prime, then add 1 to this number, capital N. And that's the end of that. And at the very end, print n. That'll be the answer. The answer is 167. So there are 167 primes of the form n squared plus 7 as n goes from 1 to 1,000. That's pretty good. Okay, well, that is the whole review sheet. So we are done.